In this lecture, we'll look at creating full JS objects. We'll look also at the importance of the this pointer and related concepts. Our JS objects thus far have been a flexible form of struct or record holding data, but full objects include methods as well. And to add methods to a JS object, we add entries whose key is the method name and whose data is a function object. Let's use as our example a linked list object, as diagrammed here with method properties add, print, and drop. Thus. Now, the object will also have data properties, head, to point to the first node on the list, and count to track the number of nodes on the list. For nodes, let's give a quick example here, and then we'll show how we build all this. For nodes, we create simple JS objects with data properties, data, and next. Call them node objects. Each node object's data property holds one data item in the list, and its next property refers to the next node object in the list. And of course, the final node's next property is set to null, which is a standard JS value that serves the same purpose that null does in Java, or capital NULL null does in C. It marks a reference as pointing nowhere. Note, by the way, that null is distinct from undefined. A reference starts as undefined upon declaration, but can be set to null. Now, this linked list object is pretty complex, and we may want to build many of them. So let's write a function to initialize it called init linked list. Its code is on lines 1 through 29 of our diagram here, as you can see. And if you're expecting a constructor, by the way, as in Java, this is the first step toward one. Now, we'll also have a test scaffold LL driver down here to create and test our linked list objects. As you can see, for instance, on line 32 here, LL driver sets up an array of two empty objects that will become our linked lists. We want several linked lists to illustrate an important concept later. And on lines 34 and 35, LL driver passes both empty objects to init linked lists, and they come back fully set up as empty lists with the two data properties and three method properties described earlier that match our diagram. So, turning to the init linked list function, we can see that lines 2 and 3 set up the two data properties with initial values. And recall, by the way, that an empty linked list has a null head pointer. Lines 5 through 8 set up the add property, add function property. This is the first example we've had of a function within another object, at least one that we've written. Since functions are data, there's nothing stopping us from making an object property be a reference to a function. And that's what sets up this thing right here. Now, the add function's code we should look at. It creates a new node object via JSON right here. It sets the data property of that new node object to the new value to be added, and it sets the next property to refer to the current first node of the list, if there were one, or it sets it to null if we're adding the first node on the list. And then it points the head data property to the new object node. So, for the first call of add with, say, val of 42, we get the result shown in the diagram here. And, of course, this.count++, or count++ here, increases count from 0 to 1 to reflect the add of the new node. But there's something else going on here. What's with all the this keywords? Here, here, and here. Now, here's a significant digression or conceptual discussion. Often, even programmers familiar with OO languages do not completely understand the mechanism by which method calls are made. This mechanism is universal to all object-oriented languages. And it's especially explicit in JS and obvious. So it's a source of frequent errors, it turns out. And it's worth going over. Consider this method call in any language. And again, consult the transcript here. List.add of 42. Now, it's expected to add 42 to the list object, of course. But here's a question for you. How many parameters does that add function truly have? That truly should signal that the answer is not the obvious response of 1. Pause and think about that. And coming back from the pause, this is actually a bit of a diagnostic. If you can confidently say 2 parameters, of course, but the first one is hidden and it's a reference to object list, then you can skip the following section. You got the idea. Otherwise, listen and read on. The abstract OO model of an object is that it's a bundle of data and methods, kind of like the rough diagram I'll show right here on the screen. Thus. And the abstract model says that each object has its own copy of the methods. This ensures that the methods of, say, object A work on object A, and those of object B work on object B, and so forth. It's a nice abstraction, but it's a lie. Copying the same code, the same method code, over and over for each of possibly thousands of objects would be senselessly inefficient. No object-oriented language does that. Instead, in every OO language, there is only one copy of any given member function, no matter how many objects there are that include that member function. And this is actually quite easy to see in JS. Let's add a second list object to our earlier diagram. As you can see, this second object's function properties point to the same functions as the first one. An important note here, when you declare an anonymous function in JavaScript, as on lines 5 through 8, only one function is ever created, even if you run those lines many times on different calls of a init-linked list. So this function sharing is the same in other object-oriented languages too. The details may vary, but the principle is the same. So this then invites the question, when I call list1.add on 42 versus list2.add on 42, how does the add function, the one and only add function, know which list it's supposed to add the node to? The answer, again in every object-oriented languages, is that add is given an extra parameter, telling it what object it's supposed to operate on, what object it belongs to for the current call. On each call, this parameter may point to a different object, and so in effect add busily makes believe it's a distinct copy for each of the different objects. But it's a shell game. The function is really being told which object to belong to on each call. This extra parameter, which is not visible in the parameter list, though I'll show it briefly here in the diagram, is called this in almost every object-oriented language, including JS. And as you can see, it's sort of snuck in there as an extra parameter. Now, the object it points to needs a name also. There's no field universal name, but in these lectures we'll call it the context object. That's one of the most important terms of the class, so be sure you understand what we mean by it. The context object is the object pointed to by this, the object on which the method is working on the current call. So, how does the interpreter or compiler determine what to pass as this? By the object you use to make the call. If you say list1.add, for instance, and assuming down here we have list thus, then list1 is passed as this. But if you say list2.add 42, then of course list2 is passed thus. And within the function, if you use a data member or property, say head for instance, then the compiler, in most languages, silently augments it to this.head. And so the shell game is complete, and you can simply believe that the function belongs to the object and that each object has its own personal copy of the function. But not in JavaScript, because JavaScript doesn't automatically add the this prefix. If you want to use this, you must do so explicitly. And you must remember to do so explicitly every time you refer to data or functions that are members of the context object, the object being worked on. And as you can see in add, we do this for every reference to head or count. Now, if you don't add this dot, then your variable defaults to a global. Say I write in the add function just head instead of this dot head, like that, on line 6. I just created a global variable named head. It's pointed to a node object that in turn points to my first node, but this dot head, which is not the same thing as head, is unchanged. JavaScript in effect says, oh, you meant this dot head and not some global? Well, why didn't you say so? This is breathtakingly bad language design, and it's one of the most common sources of bugs in JS. If you're a normal OO programmer, it will take you some time to break the habit of just referring naturally to member data or functions without a prefix. Remember to add that this dot compulsively, as you can see we do throughout the code in the diagram. So, now that discussion is done, let's get back to init linked list. The print function is next. This has a fairly standard linked list loop with the temp being marched down the list starting at this dot head, not head, and advancing via the same temp equal temp dot next assignment that you'd see in Java. C programmers, by the way, there's no arrow operator in JS. You can just use a dot. You're expected to understand linked lists as a prerequisite, but if you're rusty on them, take the time to reason through this code and review old linked list code you may have written, and then answer this question. Why is the for loop test just temp? What does that do? And coming back from a pause, temp does become null when it reaches the end of the list, either because the head was null and there were no nodes, so temp is null upon initialization, or because temp reaches the last node and temp equal temp arrow next assigns the last node's null next pointer into temp. And null is falsy, so the loop stops when temp becomes null. Now again, this isn't a linked list course, so I'll let you figure out the details of the drop function, but at least a brief overview here. Drop walks down the list, just like print does, and it's looking for a node whose data matches val. The variable prior follows temp one node behind. When temp points to the first node, by the way, prior is uninitialized. After the loop is done, temp is either null if no match was found, or it points to a matching node. In the latter case, the code on lines 23 through 26 here removes the matching node, and it deals with the special case of removing the first node on line 25 and the normal case of removing a middle or the last node on line 23. Question 3. There's a bug. Please find it and fix it. A bug in drop. Coming back from a pause there. We missed a this on line 25. And by the way, if you were thinking that there might have been a bug because prior is being tested while it might still be undefined, think carefully about that one. Undefined is falsy. So what would the effect of that bug be, the missing this dot? Would it be obvious or only show up in certain cases? What will it do when it does show up? So again, pause and come up with an answer on that. This is partly a make sure you really understand the drop list code, or the drop function code as well. Coming back from a pause there. It will show up only when we remove the first node from the list. And the effect will be to leave the first node on the list with this dot head unchanged, and also to point a global variable head to the first node. Isn't JS wonderful? By the way, assuming this is successful, what happens to the dropped node? We can no longer reach it. Does it become dead storage, as it would in C or C++? No, JavaScript works like Java. It supplies a garbage collector that periodically sweeps through memory, finding objects you can no longer reach, and marking their storage as free for new use. So C programmers, there's no need for a delete or free operation here. Now that we've got the list set up, let's go down and look at the driver. It lets you work on either of the two lists in the array via a command language with 5 commands. Add, and you give it the list number and the value to add, or drop, and you give the list number and the value to drop, or print, and you give it just the list number, or count, and give it the list number as well. And, of course, there's also quit to end. Now, most of the driver code you should decipher on your own, but line 37 has something interesting and new. That /\s plus slash in the split call is a regular expression. Regular expressions are a topic for a later lecture, but this is a brief intro to them. They're a powerful feature of JS and of many other scripting languages, and even of traditional languages like Java. They let you specify complex rules for string matching. That particular one up there matches sequences of one or more whitespace characters. Split can use a regular expression to identify breaks between strings, and using this one eliminates the multiple space problem that we saw earlier. Now a multiple space will be considered a single break. Here's a few questions on the rest of LL driver. Question 5. CMD is an array of strings after the split call. Is it okay to use a string to index array lists like that? Coming back from a hopefully brief pause. Just checking to see if you're awake here. Of course it's okay. You can't use anything else to index an array object. In this case, quote 0 quote or quote 1 quote, which would be in command 1, will pick the first or second list. Question 6. It is tempting as a traditional programmer to want to write list bracket parse int command 0 so you get an integer. Would that be a bug? Again, coming back from a pause. Interestingly, no. You'd translate the index string into a number, but we already know we can use numbers if we want to. They get automatically translated back into the string equivalent. So your parse int isn't a bug, it's just inefficient. And then a final point here. Line 47 prints the count of nodes on the list, and it directly accesses list.count. Now, as I'm sure you know, public access of member data is poor design. And most object-oriented languages let you make a member datum private to prevent such access. You write setters and getters to set or retrieve the data, and you use those instead of accessing the data directly. This lets you add any needed housekeeping when setting and getting the data, either now or in some future redesign, which is why you want to use the set-get methods instead of the public data. JavaScript, unfortunately, offers no such private scoping. You can add setters and getters, but using them is on the honor system. The language won't require it, nor block access of any property. There is a way to get privacy, but it involves closures, so we'll get to it later.